Yeah, for your quiz number 1, I'll try to return the paper back to you. If not Tuesday next week, I'll try Thursday. But before that, I'll also give you the grading scheme about how I grade the paper. So you can definitely take a look. And if you want to talk about it, more than happy to do so after you get the paper. We can talk about it. Not today, maybe later. All right. So today, my plan will be to, looking ahead. So guys, hello, please. All right. Yeah, it's gone. Okay. Hopefully it's gone a good way. All right. Okay, so my plan, we definitely want to finish the scanner as soon as we can. So today a bit, and also Thursday we're going to do lots of conversions, and then the final part will be done on Monday. And then we're going to move on to parsing. That'll be the plan. And then we got a reading week, which you got some exciting assignment about Antelope 4. After that, I'll give you the Antelope 4 assignments. You'll definitely enjoy that one. That one is going to prepare you very well for both the programming test and also the project. All right, just looking ahead. All right. So for today, I want to start with how we can, we talk about example of DFA, which we didn't quite cover in the quiz. Well, we didn't cover DFA. We didn't cover much about regular expression. It could be something we might cover later, but just make sure you don't lose that ideas. But today, we want to start with a little bit of formulation about DFA. Quite interesting to actually know how things will work formally. I will at least go over the DFA part, and then NFA, if I cannot get there, I'll do that very quickly on Thursday. Okay, let's start with DFA. You may have seen this already back in 2001. Basically, for any diagram that's drawn as a DFA, you can formulate a diagram, for example, a diagram like this. This is one DFA. You can turn this into the corresponding formulation. You can think about this part over here is like a front-end syntax, graphical syntax, but I can turn that into some intermediate representation, which is like the formulation we're going to talk about. We'll see. Okay. All right, so we got Q sigma delta Q0 F, right? Let's go over the definition here very quickly, and then I want to do the exercise with you about how to figure out how to define delta. That'll be the interesting bit I want to go over with you formally. Okay. Q will just be all the states. It's going to be a set. That one's really straightforward. And sigma will just be the input symbol, usually 0 and 1, usually. And this one, I want to pause a little bit and ask you guys. Okay? I'm pretty sure you know this is a cross product, right? What about this one over here?
It says the thing on the left-hand side. Okay.
Oh, no, just this symbol here, just for now, just this symbol. Right arrow, I know. Sure. What is that? What does that denote formally?
I don't know how to figure the whole denotes. Like, as a whole, it says that like delta is a transition function that maps from Q times E to Q.
Yes, you're not answering my question. My question is, what about just this symbol alone? What does that really mean?
I don't know.
You don't know?
I've always read it as a right arrow.
Sure. Good for you. Okay, anybody? Yes. Implies? Not quite. Implies usually, well, I know in some textbook it's actually a single arrow, but sometimes it can be double line arrow, right?
Does it denote what the output's going to be? What the type of
Yeah, it's going to tell you what the output is, but okay, maybe I didn't put the question clearly enough. It's a function. Transformation, not quite. It's a function, okay? And that's not exactly the question I wanted to ask. Let me ask you guys this. It's actually quite important, all right? Take a look at this one here, and then I'm going to give you something alternative. Okay, sorry, not this one. Okay, so the one you saw on the slides is something like, let me just be sure, it's actually Q, all right? And I'm pretty sure you guys have seen this in 1090. What? First of all, can we agree you have seen these two before? It's not really like a new symbol to you.
I've never seen this like
Really? In the math course?
no. You only have conjunction, disjunction, negation.
Oh, really? In 10?
Use negation.
I don't think that's a logic symbol.
No, it's not a logic symbol. It's about function. Mm-hmm. Really? Okay. Anybody have seen that before? If no, I can maybe show you from scratch quickly. All right? That's fine. This is so-called a total function. And this one here is something called a partial function. Okay, first of all, have you guys heard about partial versus total before? Maybe.
Probably, but with different words.
Maybe. Okay, sure.
Talking about one-to-one and non-to.
Okay, okay. How about this? Let's just focus on these two. Okay, I really want to point out, because having this rather than this, there is a reason for that. Okay? Whenever you say total function, you're basically saying whatever on the left-hand side, for every possible combination of the Q and also sigma, you must have the corresponding Q. I'm going to write it down. On the other hand, for the partial function, it is saying that for every possible combination of the states and also sigma, some alphabet, you don't necessarily need to have a Q. You don't necessarily have to have. And that's something I can maybe say a little bit more on Thursday. When you actually want to tell the difference between DFA and NFA, it's really about the difference between total function and partial function. All right, let me write it down, okay, just for your information here. This one here is to say for each combination of states, which will be a member of Q, and alphabet, which will be a member of sigma, because it's a cross product. So we're talking about all the combinations. And alphabets, there is always a corresponding states. Right? For example, let me give you another example just for analogy. Okay? You can think about addition. Addition, add, you can think about it's like from integer, cross product, integer, and then it's always going to give you another integer. Agree? Any two integer. You will never have any undefined result. Accordingly, can you think of any example that will be a partial function? Arithmetic operation. Which arithmetic operation may be undefined on its result? Absolutely. If you do division here, you still get input, integer, integer. However, not necessarily every combination of two integers will give you some defined result. For example, over here, if I say division, and then if I give you, for example, 3 divided by 0, in that case, it will be undefined. So that would be the symbol to look at, to see undefined. Okay? All right, so anyway, just for your information, for total function that we are seeing here, we're saying for any combination of the state and also alphabet, you cannot miss any of the combination. Everything must be defined. On the other hand, if it was a partial function, which would be the case for NFA, which we'll see more on Thursday, in that case, you can say it's a partial function because sometimes in a state, but you don't necessarily have some alphabet defined on that particular state to go out. Right? That's something we'll definitely see later. All right, total function versus partial function. All right, let's move on. And we got delta. And we'll talk about how to define delta in just a moment. Okay. And also we got initial state, only one starting states. And also we got a set of final state or accepting states, right? Guys, you can stare at this very quickly to see if you got any immediate question. And we're going to use these, do some example, and then do some formulation. Okay, hopefully everybody's okay. We just do one simple one to warm up. For the other one, you can definitely follow through the slides and see. Let's say this. You can think about this is what you're given as input, like a diagram. How can you turn this into the formulation over here? What should be the Q, what should be the sigma, what should be the delta, and etc. Right? That should be rather easy. I don't need to switch to iPad. Can you tell me, in this case, what would be the Q? Henry? S0, yeah, exactly. A set with two elements, S1, S0, S1. Very good. Okay, another person. How about sigma in this case? Yes?
0 and 1.
Absolutely, thank you. And what about delta? that one there depends on, I think, yeah, for this particular example, usually we use something called transition table. Okay, that's something we'll use. But there's another way to do it. But Henry, what would you like to say?
I was just gonna miss that.
Just gonna, you mean gonna list all the 4 cases? Sure, that's something I can definitely write down just for now to show everybody. So later on, if you ever got asked about the, I'll write it down first. Okay, just bear with me. Basically, you want to say you got S0 over here. If you take 0, it's going to go to S1. Okay, let me put it down here, and I'll switch in just a moment. So we are saying we got S0, and then we got 0, and then we got 1. Okay, let me show to you, and you can complete the rest. Okay. Delta is actually a function. A function essentially is a set of pairs. And here in this particular pair, we got the combination of some states and also some alphabet, meaning that if you're in state S0, and if you take the alphabet 0, it's going to move you to S1. So I really meant to say S1 here. Right, that's one way to actually represent it, and you can definitely do the rest. Another way to do it would be a transition table. I believe I have that in the slides. Well, that's actually exactly what I just listed. Okay, that's one. We can also do transition table. You can do either way if you were asked in the quiz or maybe the exam. You can say, if now I'm now in S0, I can go for either 0 or 1. If I go for 0, I'm going to go to S1, right, and etc. That's a transition table, which should be quite easy to write. Okay? And I want to revisit very quickly about the total function idea, so you can see the correspondence. If you remember what I said over here, we're going to look at all the combination of the states and also alphabets, right? So now if you go back to the transition table, you can see all the states will be S0, S1, only 2 states. All the alphabet will be 0 and 1. If you do a combination, it's going to be 2 times 2. So 4 cells you will have to fill out. Right? That's for DFA. So whenever you want to check to see whether a given diagram is actually a valid DFA, there's another way to check. You want to make sure for all the states, you got all the alphabets defined as the destination state. Okay? And the final state in this, the initial state, just 1, will be S0. And the final state, be careful, you cannot just say it's S1. It's a singleton set with S1 being the member. All right? Should be straightforward. And for your own exercise, try to turn this guy over here into the tuple. All right? That's what you can do. You got a solution over here on the slide you can check, but please do that. You might be asked something like that, which should be straightforward to answer. Okay, that's transition table. And again, you can see we got S0 until S5, we got 6 states. Multiplied by 2 possible alphabet, we got 12 entries. Every one of them should be defined. All right? And now we're going to define the transition function formally. That'll be the fun part. I want to go over it with you. Okay? We got 2 flavors to define the transition function. The second way, we're going to define that recursively. But for the first one, we're going to define in a more slightly, I'll put in quote, iterative flavor. But let's take a look. So once you're given some machine N, we want to say the language that's being accepted by machine N, right? And then that'll be basically we want to define some set over here. All right. So let's say this. We're going to do it together. Let's say we got a machine M. That's a DFA. And then we are saying that the language for the machine will be the set of strings. Each string has the form A1, A2, all the way to AN. Apparently, A1 is a character. A2 is a character. Up to AN is a character, right? And how do we actually come up with the corresponding transition function? Right? That's the question. I'll help you guys a little bit over here. Let's do the easy part. I'll give you some hints. If you got input, for example, A1, let's say you got A1, A2, A3, let's say this is your input string. Only the length is 3, 1, 2, and 3. In order for you to actually process this string by some DFA, you have to start with the initial states and then try to see where A1 is defined. For example, A1 might be defined over here, which is going to lead you to this particular state, which will be the resulting state over here. And starting from here, we're going to do A2, which might lead you to, for example, over here, and then you got another resulting states. And from here, we're going to take A3, and etc. Right? Let me help you a little bit. Given that the initial state is actually Q0, so think about we're going to start with here Q0, and then after reading the first one, we're going to get into Q1. After reading the second one, we're going to get into Q2. After reading the third symbol, we're going to get into Q3. This is kind of the relationship we want to specify. Something like this. The transition function over here should be that if you go from Q0 to A1, it should really return Q1. If you go from Q1 and take A2, it will give you Q2. If you are in Q2, you take A3, it's going to give you Q3. That's what we want to formulate over here. But how do we do that? I'll pause a little bit and let you guys think. Somehow your formulation should really think about, number one, if we are processing a string of length n, then how many states will we actually have to, well, start with Q0, and then how many resulting states should we really have, right? And then we want to say for every intermediate states, its transition is defined exactly by the delta. That's what we want to say, all right? Think about it for 1 minute, and yeah, rather than throwing back this definition to you, it might be nice to think about the process of deriving it. I can start with something here, for example. I can say, we can try to quantify the state number over here, Q0, Q1, Q2, Q3, right? Why don't we use a dummy variable I to represent them? I might say, for example, 1 less than or equal to I, less than or equal to n. That's one way to do it. You can try different range as well. Let's say if we do that. And then, what will be the final state, by the way? After an, what should be the states after an, according to the pattern? You can see over here, after A1, we got Q1. After A2, we got Q2, right? After A3, we got Q3. After an, we should get Qn. That part is easy, right? I can say Qn, after reading all the n symbols, is going to be what? What should that Qn be? It should be, yes, it should be accepting states. Thank you. But we're still missing something. We have already handled the Qn. We haven't really handled starting from Q0 all the way to Qn minus 1. How do we handle that? How do we specify them? We need delta. Before I point to Henry to see if anybody wants to give a try. Try something. Give you some hints over here. For example, over here, right? When you go from Q0 to Q1, how do you relate them? You want to say delta, right, is a transition function. Remember, it takes a state and also some symbol. So basically, you start from Q0, you take A1. That will give you Q1. And also the same delta. If you start from Q1 over here, and then you take A2, that will give you Q2, right? And so on. That's kind of the pattern. You don't have to specify so many times. Since we got a dummy variable I, it will be quite easy to specify. We just need one expression here. Given that I will be from 1 to n, right? how do we use the I to patternize this? That's why I said in some ways it's more like an iterative flavor, because you can patternize the index over here using the range of the dummy variable here. I need some expression here. Have you got an answer? Just in a moment. Yes, you want to try? Give me a give me a moment. I'll write it down. Yes. Delta, yep. I would say this one is pretty good, very good, except. If you think about here, the first value for I will be 1, agree? That means this one, well, the smallest one this will cover will be, you say Q1, and then A2, Q1, A2, and then you get Q2. You're missing Q0. We just need to adjust this formula slightly. I can let you revise one time.
Yeah, instead of QI, we had AI plus QI minus 1.
Yeah. AI, and then QI. Very good. Then that will work. So guys, I can tell you that what could be a potential question I want to fill in, maybe in the quiz. For example, I might just change the range over here. For example, what if I change the range over here? I'll say exercise for you. I might say, it might just start with maybe 0 less than or equal to I, strictly less than n. How would you change that form accordingly? Think about it, all right? All right, so if I reveal that, it's going to be exactly the definition that we got over here, all right? It's a very standard definition, but maybe you never thought about maybe that deeply, like how it was derived. The insight really is, for any given string of certain length, you want to start with Q0. Before that, after handling the first character, it will be Q1, and etc. You want to use the delta to specify it. All right? A little bit dry, but I think it's important to make sure you understand that foundation. That's very good. Yes?
Can you go back to that again?
Of course. I mean the iPad notes?
Yeah.
There we go.
It says that AI. Oh wait, never mind. Fine. I got some symbols mixed up.
No worries.
Cool.
That's absolutely fine. Okay? Yeah, so any string that's not here should not be in the language, so that should be rejected. Basically, any string that would be undefined at some point by the transition function delta, that should be rejected. All right? Okay, I'll just keep track of the time. All right. All right, so that's another intuition. You can take a look. All right, and let's try another flavor of the definition. I believe that's what Henry likes, recursion. But before I point to him, we can think about how we can define delta recursively. Okay. What we want to do is to extend the delta here to delta hat. You can see there's a hat over here, the red one. Okay, what it will do is it's going to, okay, it's a bit different, right? You can see the normal delta will take just sigma, but now it's sigma star. That's the only difference. What does that mean? That means the delta hat is a generalized version of delta in such a way that it will take just a single state, the starting state, and then a sequence of characters, like a string, and then move maybe many states ahead according to the transition function. It will return to you just a single state for DFA. Later on, when we try to formulate the NFA, it's going to be more complicated, which we'll deal with quickly on Thursday. So this is the delta hat that we want to define. Once we got a definition for delta hat, it'll be easier to think about what language will be accepted by a given DFA. All right? Well, the way to define delta hat would be to do it recursively, right? So we want to think about recursive definition. So I'll already put it down for you. So we want to define delta hat, right? Delta hat over here. We got base case, just empty string. That'll be the base case. I'll try to compute this function to trace it together with you once more as well. Okay, but let's do that later. This will be the base case, and this will be the recursive case. And this is how you understand the recursive case. It's going to be a single string. But you can break the string down into two parts, into the last character A plus the preceding part of the string. All right? So let me just show to you. The A here is really the last character. And this will be the like a preceding string, like a prefix of the string, basically. All right? We just need to find out the definition for these two. Okay? Why don't we start with the easy one? If I'm now in Q, I take no character, where should I be? If I'm here, initial state, for example, I don't take any input, where would I be? Yeah, exactly, just the same state, right? That one's obvious. Don't think too much. That one's very obvious. All right? Base case. All right? If in your states, in a particular state, don't read anything, you're just in the dead states. What about the recursive case over here? This will be the interesting bit for everybody to think. And my hints to you. Break down the string into two parts, which I already explained. You want to handle this part over here and also this part over here, which is a single character, separately. And in your definition, of course, you may have to call the delta head recursively. Right? It's more like defining a recursive method in Java. Right? Anyone would like to give a try? William? Yes, I'm going to write down whatever you say. Go ahead.
All right, so I guess it's going to be equal to delta.
Delta, I like it.
Of our first input is going to be delta hat.
Okay.
Q of x. X, and then close that off, and then A.
Yeah, fantastic, perfect.
Really?
Yeah. It's not difficult, right? But maybe you never actually try to derive this, on your own.
I'll be honest, this makes no sense to me, but it's also the only possible next step.
That's okay. Sometimes, when you have no option, maybe the only option might be the other one. Okay, anyway, let's try to understand this, right? Don't lose the big picture. We are trying to define the recursive case for delta hat. Because it's a recursive case, we have to still use delta hat at some point. So here, delta hat over here, also delta hat over here. But as we learned back in Java course, recursion will be invalid if you don't really make the input strictly smaller. But we are making it smaller. Rather than handling XA, we are now handling just X. So we got one character strictly smaller. So that's okay. For sure, it's going to terminate at some point. And then, so that means we're going to handle just X. Let's put it in this way. Let me draw the diagram for you. We start with Q. And then we want to take some string X, which will lead us to some intermediate state, maybe Q prime. You can think about this guy over here is Q prime. And then we're going to take the last mile, last bit, A. That will give us to the final states, which is exactly this part over here. That will be some visual for you. But the visual for NFA will be actually more complicated. So let's understand DFA first. All right, and there would be some exercise that we can do together to see how we can unfold delta hat. Let's do it together. All right. So let's say I want to do delta hat, and then I will start with, let's say this is a DFA we know about, alternating zeros and ones. We'll start with S0. We want to handle 0, 1, 0. We want to know where the final state is. Obviously, you can look at the diagram. 0, 1, 0 is going to be S1. But how do we use the computation of delta hat definition? That's important. All right? Let's do that quickly. You're going to break it down into two parts, 0, 1, and also 0. Right? So what we're going to do is it's going to be delta hat. First of all, delta. And then it's going to be delta hat, and then S0, 0, 1. And then you're going to take the last bit over here, which is 0. Can you see the correspondence here? Okay, you can see here, 0, 1, 0, 1, still computed by delta hat. And the last bit can be computed just by delta. All right? Delta can only handle one character at a time. And this is not simple enough for the delta just yet. Right? Let's do it again. Okay, this one here, just for this part, is going to be, let me choose a different color. This part here is going to be delta hat, and then, oh, sorry, just delta, beg your pardon. Delta here, so delta hat, and then we're going to get 0. Oh, nope. What should this be? What should be the starting states? Should it be the initial state, right? We're still talking about a prefix, right? So it will still be S0. And then it will take only 0 over here. And then the final character will be just 1. Okay? You got to keep unfolding. What you need to do ultimately is to see, is this really the base case just yet for delta hat? Not really, because we're expecting epsilon. Not yet. Okay? Exercise for you. Exercise. Finish unfolding this. And the final answer should be, because we're going to do 0, 1, 0, S1. All right? That's something I want you to do. Okay? And ultimately, once we got the delta hat, how do we define the language for the DFA? Right? I'm going to reveal that right away. Okay? Just to, it's going to be something like this. Okay? Let's read it together. The language of some DFA machine M is going to be all the strings that will be accepted by the DFA. But what does it really mean to be accepted? That means the string must be sigma star. It must be a valid string with all the alphabets. And the delta hat we're using, we start with Q0, which is the initial states. And then W itself will be processed. The return states, the return value over here is a single state. That should be one of the accepting states, F. For example, in this case, after processing 0, 1, 0, we simply return S1. S1 is not one of the final states, so that's not being accepted. If the return state is either S3 or S4, it will be accepted. Right? A little bit abstract over here, but as a foundation, we have to just get over. Do you guys have any question about this? We okay? Okay. All right. Okay, so that's good. Formulating DFA, I'll leave that to you. Okay, now we can move on to NFA. Okay, I'm not going to trouble you with the NFA. Everybody might be tired about its formulation. We'll do that the first thing on Thursday. All right? Maybe not now. Otherwise, everybody will fall asleep. That's okay. Understandable. But we'll just do NFA. And for NFA, I just want to do quick example and trace one string. And that's it. So you have the intuition. What's really the difference between NFA and DFA? Quick exercise for everybody. I think we did something similar, but not exactly the same. I don't think that's the one you did, William, right, in the class. I don't think that's the one. You did something similar. Anyway, that was the one? Yeah. Okay. Was it the one?
No,
it ends with 0, 1. Is it contains 0, 1 or end? Okay, but this one ends with 0, 1. Slightly different. Okay. So guys, draw very quickly. Just take 1 minute. Should be easy to draw. I want a DFA that is going to accept any string which will end with 0, 1. Not contains, but ends with. This could be a nice example to show there are occasions where it's easier to specify NFA, but not DFA. Slightly easier, or sometimes much easier. Yeah, just hang on. Okay, I'm gonna share the answer. Okay, that should be something you will get, right? Something like this. Am I right? Of course, you have to make sure from every state you will get exactly 0 and 1, just once. Cannot be more than one. Has to be exactly once. 0, 1, and then except that, I think I should put 0 here. Okay? That's what you had to draw for DFA. Let's have some very quick observation over here. The idea would be, it would be very nice if somehow we can know where we are reaching this part over here. You can see it will be preceded by some string, some prefix x. After the prefix, you're going to do the ending 0 and 1. It would be very convenient if we can know where this point is. But for DFA, it's kind of hard, right? For example, let's say this. Simplest string, that will be accepted. We just get 0 and then 1, and it will be accepted right away. But what if we got something like this? Let's say it's 0, 1, 1, 1, 1, 1, and then 0, 1, right? Let's say we got 0, 1 over here, the 0, 1, 0, 1 over here. So now we thought we might be accepting, but we got more to read. In that case, we will have to go back over here and hoping that at some point 0, 1 will happen again. So this is actually some inconvenience for the DFA. You want to be precise where you are. You don't really allow what they call non-determinism. For NFA, we have that kind of flexibility for you. Okay? Basically, for this particular state, we don't really have the flexibility to say it can represent two things. Either it's actually before, right before this point, when we take 0, 1, or it may be not before this point. We want to be a little bit more unsure. That's kind of the non-determinism. For NFA, let's try to see. The NFA is going to be something just like this. That means we're going to go for 0 and 1, so that would be accepted. Before that, you can take as many 0s, 1s as you like. The orange one over there is not a DFA, obviously, right? How do you know? Well, let me just tell you right away, and then we can see one connection to the transition function. Let me talk about it as well. For example, let's say for this particular state, let me talk about this. Let's say S1, S0, S2. You can see S0 over here, S1. If I say S1 and also 1, is this input defined in the transition function in this case? Oh, sorry, S1. I meant to write 0. Beg your pardon. Not really, right? Because at this point over here, you actually don't really have any 0 defined. But we said before, in order for that to be a DFA, it must be a total function, meaning that every combination of the states and also alphabet must be defined. But it's not the case over here because we're missing S1 and then 0. So that's not DFA, first of all. All right? Not DFA. But it is, this kind of a non-determinism will actually give us some flexibility for specifying something that we'll see later. Okay, NFA. Okay, you can miss some alphabets. What I want to do is just to try to see how we can trace some NFA, and that'll be it for today. Okay. Okay, I think, you know what? It's actually already 3:45. That's where I want to end it. Okay, how about this? Let me stop here, and then you guys should really read up to 31. So for Thursday, I'm going to move a little bit faster. We really want to finish the scanner part, and we want to move to parsing as soon as we can. Okay, so for Thursday, the plan will be we want to at least finish formulating NFA. We want to do conversions, and then there might be just one topic left, which will be until Monday, which is about minimizing DFA. That's what we'll do. Okay, but just make sure you catch up with the study here. I'll try to return your quiz 1 number paper maybe next Tuesday or Thursday. I'll try. All right, see you on Thursday.